Hello my friends, and welcome back to the You Can Do TV channel. The El Paso 1 project is a significant border infrastructure initiative spanning 46 miles near Deming, New Mexico. On January 28th, concrete pouring and laying operations were in progress, with close-up shots capturing the freshly dried sections. This project is part of a broader effort by the U.S. Army Corps of Engineers South Pacific Border District, which is overseeing the design and construction of border barriers across California, Arizona, New Mexico, and Texas. These projects are funded by the Department of Defense and executed at the request of the Department of Homeland Security and Customs and Border Protection. Concrete barriers play a crucial role in border security by reinforcing physical deterrence and enhancing operational efficiency. The initiative aligns with federal directives to strengthen border infrastructure while adhering to engineering and safety standards. The ongoing construction underscores the collaboration between various government agencies in implementing security measures along the southwest border. Notably, the footage confirms that no individuals in the images cross the international border, emphasizing the project's focus on structural development rather than enforcement activities. Construction process of Fishers-Bollard fence. Construction process of Fishers-Bollard fence begins with equipment positioning within the 60 feet Roosevelt easement. A truck delivers the required materials, and the first set of 7 18-foot panels is loaded. Wire mesh is then installed on the lower angle iron. A machine swings 56 feet of fence into the trench, followed by precise alignment. Once the concrete truck arrives, concrete placement begins, ensuring no movement of the bollards or mesh. The second set of 18-foot fence panels is then installed. Next, the first set of 30-foot fence panels is positioned in the trench, followed by the loading and installation of the final 30-foot panels. Roller compacted concrete is placed to complete the foundation. In total, 192 feet of bollard fence is installed within the designated area. After allowing the concrete to cure, the excavator is stripped away and repositioned for the next phase of construction, ensuring a continuous and efficient workflow. The full installation process of the border wall by DeWind begins with site preparation and logistical coordination. The process requires specialized trenching equipment, custom-built to facilitate the continuous installation of a stable foundation adjacent to the border. The first step in foundation construction involves the removal and repositioning of temporary wall panels each day. This ensures that border security is maintained while allowing construction to progress. Once the site is prepared, the one-pass trencher excavates a trench measuring approximately 6 feet wide and 8 feet deep. As the trencher moves forward, it simultaneously mixes the native soil with Portland cement powder and water, creating a homogeneous, reinforced foundation. Material handling is a crucial aspect of the process. Dry Portland cement is delivered to the site via trucks and transferred to the trencher through a blower system. The cement is metered into an auger bin, which dispenses the precise amount into the trench. Large water tanks supply the necessary moisture for the soil stabilization process. The trencher's high-speed digging chain ensures even distribution of the cement mixture, while skilled operators meticulously guide the machine along the alignment, placing marker stakes to maintain accuracy just 2 inches from the border. Once the foundation has stabilized, the next phase involves surface preparation for wall panel installation. The top 12 inches of soil are removed, creating a level platform for panel placement. A smaller trencher then cuts a precise trench down the center of the foundation to accommodate the permanent wall panels. These panels are set into the key trench and secured with concrete, ensuring structural integrity and long-term stability. By utilizing one-pass trenching, the installation process is streamlined, reducing equipment needs and expediting construction. This method provides a reinforced, seamless foundation that enhances border security while maintaining efficiency and precision. This section is about king sheet pile wall construction, an innovation for the infrastructure stabilization scheme. First, longer-length king piles are partially driven into the ground to provide initial support. These king piles serve as primary structural elements, allowing the placement of shorter, intermediate piles between them. Once the intermediate piles are installed, the king piles are driven to their final depth, ensuring a secure connection and maintaining alignment. This method prevents deformation and ensures tolerance for subsequent pile installations. Specialized equipment, such as the ABI-TM-20 long-reach telescopic leader rig, enhances precision during installation. The process stabilizes infrastructure by reinforcing embankments and preventing soil movement. Proper execution of the installation ensures long-term structural integrity, making the king sheet pile wall an effective solution for embankment stabilization in challenging conditions. The construction of the Chenab Bridge, part of the Udhampur-Srinagar-Baramulla Rail Link (USBRL) project, presents one of the most challenging engineering tasks in India. Spanning the deep gorge of the Chenab River between Bakal and Kauri in the Riasi district of Jammu and Kashmir, the bridge will stand at 359 meters above the river, making it the tallest railway bridge in the world. The construction began with extensive geological surveys and slope stabilization efforts due to the young and unstable Himalayan rock formations. To ensure stability, experts from the Indian Institute of Science, Bangalore, designed slope stabilization measures, which were verified by international consultancy URS. The initial phase involved tree cutting, development of dumping yards, and constructing access roads to facilitate movement of heavy machinery. Nearly 5 kilometers of roads were formed on the Bakal side and 3 kilometers on the Kauri side to support construction operations. Excavation of the foundation was executed using a top-down method to enhance safety. The slopes, varying between 43 degrees and 77 degrees, required controlled blasting techniques to prevent rock mass damage. Pre-splitting, a technique involving precise drilling and minimal explosives, was applied to create accurate excavation profiles. Once blasting was completed, heavy equipment such as excavators, jackhammers, and dumpers cleared the debris, which was transported to designated disposal sites. To reinforce the excavated slopes, rock bolts of varying lengths, 4 meters, 8.5 meters, and 11.5 meters, were installed. A layer of shotcrete with steel fiber reinforcement was then applied to the slopes to enhance stability. Drainage systems, including weep holes, were incorporated to prevent hydrostatic pressure buildup. The foundation for the bridge's piers required massive reinforced concrete footings, with the tallest pier reaching 137 meters. Given the complexity, meticulous planning was crucial to synchronize excavation, stabilization, and construction activities. Construction equipment consumed approximately 15,000 to 18,000 liters of diesel per week, necessitating a well-coordinated logistics supply from Riasi. The bridge is engineered to withstand extreme environmental conditions, including seismic activity of magnitude 8 on the Richter scale and wind speeds of up to 90 kilometers per hour. Sensors installed on the bridge will automatically halt train operations if wind speeds exceed safe limits. Designed for contact blast resistance, the bridge employs cutting-edge technology to ensure longevity and resilience. Upon completion, the Chenab Bridge will not only be the highest arch railway bridge in the world, but also a testament to India's engineering prowess, connecting remote regions through one of the most ambitious railway infrastructure projects. DeWind one-pass trenching utilized its Montana 4500, the world's largest one-pass trencher, to repair the dam at Lake Hope in New Plymouth, Ohio. This machine, with 4,500 HP and over 1,500,000 pound-feet of torque, trenched to a depth of 70 feet to install a continuous underground barrier wall. The process involved cutting through various soil layers while simultaneously mixing a specialized slurry with the excavated material. This mixture solidified within the trench, forming a uniform, watertight wall beneath the dam. Unlike traditional methods that require extensive material handling and grout pumping, DeWin's system performed all mixing directly in the trench. This eliminated the need for additional equipment, reducing logistical challenges and improving efficiency. The uniformity of the wall ensured consistent composition, preventing weak points that could lead to seepage. Working within a confined 30-foot wide access area, the trencher efficiently installed the wall while minimizing disruption to the surrounding residential area. The one-pass method allowed for high production rates, reducing the overall project timeline while maintaining structural integrity. This approach resulted in a durable, precisely mixed cut-off wall, reinforcing the dam's stability and ensuring long-term water retention. The construction of Anaram Barrage was a crucial part of the Kaleshwaram Lift Irrigation Scheme, KLIS, aimed at harnessing the water of the Godavari River to support irrigation, drinking water supply, and industrial needs in Telangana. The project was awarded to Afcons many years ago with a tight deadline of 24 months, requiring meticulous planning and execution. The initial challenge arose when the location of the barrage was shifted, extending its length to 1,270 meters. This necessitated a fresh geological survey, revealing varied subsurface conditions, including sand, silt, gravel, and hard rock. Consequently, sheet piling was replaced with cast-in situ secant piling for the cutoff foundation, marking a global first in barrage construction. Construction proceeded under extreme climatic conditions, with temperatures reaching 50 degrees Celsius in summer and floods during monsoons. The team deployed advanced machinery to expedite work, consuming 1,500 tons of cement and 200 metric tons of steel daily. Concrete pouring reached 5,500 to 6,000 cubic meters per day, culminating in over 1 lakh cubic meters per month for 4 consecutive months. Anaram Barrage features 66 radial gates, each 15 meters tall, supported by 72 piers of 24 meters height. A 7.5 meter wide road bridge runs atop the structure. With a storage capacity of 10.87 TMC, the barrage plays a pivotal role in regulating and lifting water to higher elevations for agricultural and domestic use. The installation of the Incity Tower spire in Lyon was a complex engineering challenge that required precision and coordination. On Sunday, June 21st, the final 2 segments of the spire were successfully lifted and positioned using a helicopter. This metallic structure, measuring 50 meters in height and weighing 25.9 tons, brought the tower to its final height of 200 meters, establishing it as the tallest building in Lyon and the 3rd tallest in France. The spire was composed of 4 individual elements, each varying in weight from 2.5 to 14.7 tons. Given the constraints of working within an urban environment, a helicopter was chosen as the optimal lifting method due to its ability to provide precise aerial maneuvering in a limited space. The operation involved careful logistical planning, including the coordination of ground crews, aerial specialists, and the structural team responsible for securing the spire to the tower's framework. The lifting process required extreme accuracy, as each segment needed to be precisely aligned before being affixed to the tower. The helicopter, operated by an experienced crew, hovered above the structure, guiding each component into place, while ground teams ensured proper alignment and bolting. The final attachment process required securing the spire firmly to the existing tower framework to withstand environmental factors such as wind and structural vibrations. Following the spire's installation, additional elements, including 3 aerial beacons and a lightning rod, were mounted at the top. These components serve essential functions, providing aviation safety signals and protecting the tower from lightning strikes. The completion of this phase marked a significant milestone in the construction of Incity Tower, reinforcing its architectural signature in Lyon's skyline. The project was executed by Bouygues Bâtiment Sud-Est and Bouygues Bâtiment Île-de-France, with architectural design by Vallaud and Pistre and AIA Architectes. The tower was developed by Sogalim Dixons and is owned by Caisse d'Épargne, Rhône-Alpes, and SNCF. Delivered in December many years ago, the Incity Tower remains a landmark of modern construction and innovative engineering. The VG Mastermatic is the centerpiece of the Langley Concrete Group's Chilliwack production facility, providing fully automated, high-efficiency precast concrete pipe manufacturing. The process begins with the automated filling of pipe molds, precisely controlling material placement for uniform density and strength. The machine then presses spigots onto the pipes, ensuring precise dimensions and structural integrity. Once formed, the pipes are automatically offloaded and placed onto steam kiln carts for controlled curing. A unique feature of the Mastermatic is its moving floor system, which transports freshly molded pipes into a large inline kiln. This kiln utilizes controlled steam temperature to accelerate curing, allowing the pipes to achieve strength equivalent to a 14-day cure in just one night. This rapid curing process enables quick delivery to meet urgent project demands. The Mastermatic provides unmatched production flexibility, capable of manufacturing 3 small diameter pipes, 300 to 450 millimeters, simultaneously 2 mid-range pipes, 450 to 600 millimeters, or a single large diameter pipe, 675 to 1,200 millimeters. Additionally, it can produce both reinforced C76 and non-reinforced C14 pipes in parallel, allowing Langley Concrete Group to adjust daily output based on customer needs. Post-curing, the system automates pipe handling, including pallet stripping, cleaning, and quality control inspections. Automated measurement, marking, and data printing ensure each pipe meets industry standards before dispatch. The integrated automation reduces manpower requirements by over 50% compared to conventional production methods, making the process both cost-efficient and highly productive. With the capability for 24-hour operation, the Mastermatic significantly increases production speed and volume without compromising quality. Its combination of automation, precision, and efficiency makes it a cornerstone of modern, precast concrete manufacturing. The construction of the Fortescue River gas pipeline involved the installation of a 270 kilometers, 16-inch diameter pipeline to transport natural gas from the Dampier to Bunbury natural gas pipeline to TransAlta's power station at the Solomon Hub. The process began with route surveying and land clearing, followed by trench excavation. Pipe sections were welded, inspected, and coated to prevent corrosion before being lowered into the trench. After backfilling, hydrostatic testing was conducted to ensure integrity. Valve stations and compression facilities were installed for operational control. The final phase included commissioning and system integration with the power station. The project provided a critical energy infrastructure link to support mining operations in the Pilbara region. The installation of tight wells follows the PN 1610 standard, which defines the principles for constructing and testing sewer pipes. The foundation of the well must be designed individually, considering local water conditions. During leveling, the actual thickness of the bottom slab should be verified on-site. The type and degree of compaction of the bedding must meet design requirements, with a recommended compaction index of at least 0.98 and a secondary deformation modulus not exceeding 2.2 times the primary value. Proper ground leveling is crucial to ensure the bottom slab is securely seated. When connecting pipes to the well, an appropriate lubricant should be used on the sealing transition, gasket, and pipe end. Substitutes such as dishwashing liquid or industrial pastes are not permitted. The pipe must be inserted into the sealing transition centrally. Factory-supplied well components require the correct use of spherical lifting slings for transport and assembly. Chain lengths must be appropriate to avoid damage. Rings and reducers, lacking built-in transport systems, must be handled using designated lifting equipment per manufacturer guidelines. During assembly, surfaces must be cleaned, and gaskets lubricated to ensure proper sealing. Components should be placed centrally and aligned, allowing them to settle under their own weight. How to install and remove sheet and frame at Mobe EMV installation. The installation process begins with securing all hoses and lines, ensuring a safe and efficient connection to the excavator-mounted vibrator, EMV. Once secured, the EMV hookup is completed, allowing the equipment to function properly. A final inspection confirms that the system is ready for action before proceeding with the frame and sheet installation. Frame installation. Frame installation starts with careful preparation, ensuring that all components are properly introduced to the site. Precise measuring is essential to align the frames correctly within the excavation. Leveling follows, ensuring a stable foundation for the trench support system. Once all adjustments are made and stability is verified, the frame installation is complete. Sheet installation. The first side of the trench sheet or sheet pile is installed carefully, ensuring it is correctly positioned within the excavation. Corner installation is then completed, providing additional reinforcement and stability. Finesse and control are required throughout the process to secure the sheets properly. Once all sheets are in place, the installation is finalized. Sheet removal. The removal process is conducted systematically using the EMV or appropriate extraction equipment. Sheets are carefully extracted one by one to prevent ground disturbance and ensure site safety. Once all sheets and frames are removed, the area is inspected and the site is cleared, leaving it ready for the next phase of construction. The Jammu-Udhampur Highway is a crucial segment of National Highway 1A, connecting Jammu and Kashmir to the rest of India. Given its strategic importance for both defense and civilian transport, the project aimed to upgrade a 65-kilometer stretch by constructing tunnels through hills and bridges across valleys. The improved highway significantly reduces travel time from 2 hours to just 45 minutes, enhancing connectivity and boosting regional economic growth. One of the primary challenges was constructing bridges and tunnels in the hilly terrain. To expedite the process, standardized bridge spans were introduced, allowing for precasting of superstructures in site factories. This innovation reduced construction time while ensuring structural strength and quality. Additionally, numerous tunnels had to be excavated through the mountains, requiring advanced rock-cutting techniques. Instead of traditional blasting, an L-cut drum cutter was used for precise cutting, supported by road headers, which increased efficiency and minimized environmental impact. In tunnel construction, conventional concrete linings were replaced with steel fiber reinforced shotcrete, SFRS, applied in layers along with lattice girders. This method eliminated the need for a time-consuming concrete lining process while maintaining tunnel stability. Additionally, in areas with steep gradients, traditional hairpin bends were avoided by cutting hills up to 40 meters and raising valley sections by 50 meters to create smooth road curves that support vehicle speeds of at least 60 kilometers per hour. To protect the road from landslides and rockfalls, multiple retaining wall techniques were implemented. RCC walls, gabion walls, and soil stabilization measures were used depending on the terrain conditions. These structures ensured long-term stability and safety for travelers. Moreover, environmental and social considerations played a crucial role in the project. The road alignment was altered near a wildlife sanctuary, a major water pipeline was rerouted without disrupting supply, and a local temple was preserved by adjusting the road design. Traffic management was another significant challenge. Despite the ongoing construction, at least 2 lanes were kept operational at all times to ensure minimal disruption. The workforce of over 8,000 workers operated day and night, with incentives provided for on-time completion of tasks. The Poso Dua Hydropower Plant, a 195 megawatts run-of-river project, is located on the Poso River in central Sulawesi, Indonesia. Developed by PT Poso Energy, this project plays a crucial role in providing renewable energy to the region. The plant consists of 3 Francis vertical turbines, each with a capacity of 65 megawatts, and has been operational since its commissioning in 2012. Project overview. The Poso Dua Hydropower Plant was developed as a single-phase project and remains one of the most significant hydropower initiatives in Indonesia. The project's total investment reached approximately $288.6 million, highlighting its scale and importance. The power generated from the plant is supplied to Point PLN Persero under a long-term power purchase agreement. The plant generates approximately 1,195.74 gigawatt-hours of electricity annually, contributing significantly to the region's energy supply. Design and engineering. The Poso Dua facility operates with a net water head of 150 meters, and water is channeled through a penstock system that is 786 meters in length and 36 meters in diameter. The hydropower station is equipped with 3 electric generators, each with a capacity of 72.2 MVA. The frequency of the power generation system is 50 Hz, ensuring compatibility with Indonesia's electrical grid. As an EPC, engineering, procurement, and construction project, the development required comprehensive planning, equipment procurement, and rigorous quality control. The project implementation involved key phases such as equipment design, procurement, on-site installation, and commissioning. Construction process. 1. Early stage and site preparation, 2016-2017. The initial groundwork for the Poso Dua hydropower plant began in mid-2016. Excavation and land preparation for critical structures, including the powerhouse and dam foundation, were undertaken. June 2016. Excavation work started at the powerhouse area. August 2017. Mobilization of key components, including spiral cases for the power station. September 2017. Construction of the weir, intake system, and waterway infrastructure commenced. 2. Civil and Structural Works, 2017-2018. By 2017, major civil works were in progress, including the construction of the head race tunnel, anchor blocks, and expansion joints. September 2017, installation of key hydropower components, including the penstock system and powerhouse structures, began. October 2017, the powerhouse and substation were under construction, with efforts focused on structural reinforcements. February 2018, key elements such as anchor blocks for the head race tunnel, surge tanks, and expansion joints were installed. Three, Mechanical and Electrical Installation, 2018. The project progressed into the installation phase, focusing on the turbine systems, generators, and supporting electrical infrastructure. April 2018, the extension of PLTA Poso 2 and the installation of power transmission systems continued. Testing phase. A series of dynamic and static load tests were performed on the gantry crane and other structural components. Challenges and quality control measures. Developing a large-scale hydropower project in a remote location posed multiple challenges, including logistics, supply chain management, and environmental considerations. To address these issues, PT Poso Energy implemented strict quality assurance measures, establishing a dedicated project management team to oversee the entire EPC process, ensuring smooth coordination among various suppliers and contractors. Conducting rigorous equipment testing and quality inspections to maintain high operational standards. Ensuring timely procurement and delivery of materials to prevent construction delays. Monitoring and mitigating environmental impact through responsible engineering and operational strategies. Implementing strict safety protocols to ensure worker safety throughout the project timeline. Operational benefits and impact. Since its commissioning in 2012, the Poso Dua hydropower plant has played a vital role in electrifying Central Sulawesi and South Sulawesi. The project's success has brought multiple benefits. Renewable energy supply. The hydropower plant contributes to Indonesia's renewable energy targets by generating clean electricity. Economic development. The project has created jobs during its construction and operational phases, boosting the local economy. Infrastructure enhancement. The development of the plant has led to improvements in transportation and logistical networks in the region. Stable power distribution. By supplying electricity to Point PLN Persero, the plant has helped stabilize the power grid and reduce dependency on fossil fuels. The construction of Monaco's offshore extension aimed to create 6 hectares of new land while minimizing environmental impact. The project involved a reclaimed landmass surrounded by reinforced concrete caissons placed on a submarine embankment. Environmental measures included relocating marine species, controlling turbidity, and monitoring noise levels. Dredging removed polluted sediments, which were transported to a treatment center, while clean sediments were relocated at a depth of 200 meters. The foundation was built using quarry materials delivered by specialized vessels. "18 massive concrete caissons were fabricated in Marseille and floated to Monaco for installation. After securing the caissons, the land reclamation continued using stone materials. The project stayed ahead of schedule, allowing early infrastructure work. The completed platform will serve as the base for the eco-district of Portier Cove. This is about the seawall reinforcement project at Haifa Port. This involves advanced construction techniques to secure the waterfront infrastructure, ensuring durability against harsh marine conditions. Workers are actively replacing a seawall by driving steel sheets into the ground to reinforce coastal protection. The process involves positioning steel sheet piles and driving them into place using vibratory hammers. These interlocking sheets form a continuous barrier, preventing soil erosion and water infiltration. Proper alignment and reinforcement ensure long-term stability. Once installed, the sheets are capped with concrete or steel beams for added strength. The rehabilitation of Mahatma Gandhi Setu in Bihar was a landmark infrastructure project aimed at strengthening one of India's longest river bridges. The project, executed by AFCONs under the Ministry of Road Transport and Highways, involved replacing the deteriorated RCC superstructure with a new steel truss superstructure, making it the first instance in India where a balanced cantilever bridge was converted into a simply supported bridge. To manage traffic during construction, vehicles were diverted to the downstream section, and a pontoon bridge was installed to accommodate light vehicles. The dismantling phase required precise execution to minimize environmental impact, especially as the bridge spans the ecologically sensitive Ganga River. Over 75,000 cubic meters of concrete were removed, using wire saw cutters for spans over water and high-reach boom jaw cutters for sections over land. Anti-dust suppression systems were employed, and debris was carefully lowered using cranes and gantries before transportation for reuse or disposal. The installation of the new steel truss superstructure involved erecting 720-ton segments between modified pier caps. Ground support systems were used for spans over land, while cantilever erection methods were applied over water. The high-performance steel structure, using 66,360 metric tons of steel, ensures a 100-year lifespan for the bridge. The Chenab Port expansion project, the largest of its kind in West Africa, has undergone several critical construction phases, led by Meridian Port Services, MPS. The project involved reclaiming 90 hectares of land from the sea, constructing a 3,500-meter breakwater, and dredging over 4 million cubic meters to deepen the harbor basin. China Harbor Engineering Company executed the marine works, including a 700-meter quay wall. Lafarge completed earthworks, drainage, electrical installations, and paving. Rails were installed for gantry cranes, while Consar handled the construction of terminal buildings. In December, 27 gantry cranes, including 7 ship-to-shore cranes, were delivered to facilitate container handling. The port is designed for future expansion, with high-tech infrastructure ensuring efficiency. As final installations and data systems are completed, Chenab Port is set to become a leading maritime hub in the region. Seawall construction with concrete blocks in the United States is a critical infrastructure project aimed at protecting coastal areas from erosion and storm surges. Typically, these seawalls are built using precast concrete blocks, each weighing between 2,000 and 10,000 pounds, depending on design specifications. The construction process begins with site preparation, which includes excavation and foundation stabilization, using crushed stone or geotextile fabric to prevent settling. The concrete blocks, often measuring 3 to 6 feet in length and 2 to 4 feet in height, are then carefully placed using cranes or hydraulic lifting equipment. For added durability, blocks are interlocked or reinforced with steel rods and filled with concrete grout. Seawalls in the United States are typically built to a height of 8 to 20 feet, depending on wave conditions and local regulations. Many projects, such as those in Miami and New York, incorporate wave-dissipating designs and additional riprap for strength. A well-constructed seawall can last 50 to 100 years with proper maintenance. Marco Polo is a large floating metal structure, known as a caissonier, built by Bouygues Construction. Measuring 61 meters long, 52 meters wide, and 27 meters high, it has been operating in the Grand Port Maritime of Marseille since September. Marco Polo produces the 18 caissons that will form the protective barrier for Monaco's new eco-district, Anse du Portier. The first caisson has now been completed, marking a significant step in the project's progress. The construction of the 4 kilometers long, jointed unreinforced concrete road in Silivri followed a systematic process to ensure durability under heavy traffic conditions. The roadbed was first leveled and adjusted according to project specifications. Concrete, produced at a ready-mix plant, was transported to the site using dump trucks and distributed into the paver's hopper with an excavator. The concrete, classified as S1 slump, was compacted using vibrators in the paver. A slip-form paver was used to lay the concrete at the designated width and 25 centimeters thickness. Initial surface leveling was performed automatically, followed by manual finishing with steel screeds. To enhance skid resistance, the surface was textured using a broom finish. After finishing, the entire concrete surface, including side edges, was coated with a resin/acrylic-based curing compound. In adverse weather, burlap and tarpaulins were used for protection. Expansion joints were marked and cut within 24 hours of placement to control shrinkage cracks. This process ensured a durable, long-lasting, and cost-effective concrete road. The construction of 2 20 meters diameter circular gravity cofferdams at Great Yarmouth Harbor involved a pre-assembly and float-out method to minimize disruption and account for fast tidal currents. First, a robust temporary support frame was fabricated on the quay side, with straight web sheet piles interlocked around it and secured at the upper level. A jack-up piling barge was positioned at the installation site while a sheer leg crane barge lifted the 400-ton pre-assembled cofferdam structure. Using GPS positioning, the structure was floated into place and lowered onto the seabed. 8 660 mm diameter tubular piles were vibrated 5 meters into the seabed to anchor the structure securely. The sheet piles were then driven to the design tow level using a vibratory hammer. Finally, sand pumps hydraulically placed fill material inside the cofferdam. This efficient construction method ensured both cofferdams were completed on schedule by August without disrupting harbor operations. The installation of the Rockland Street and Burke Village Promenade storm sewer involved laying over 1 kilometer of reinforced concrete pipe. Gemco Construction installed 900 meters of 1,800 millimeters ASTMC 76CL3 pipe, along with 100 meters of 1,500 millimeter and 200 meters of 600 millimeters pipe. The process included placing 1,800 millimeter miter bends, 17 tee-off manholes, and 25 Y-off service connections. The pipe installation process begins with inspecting delivered pipes for defects such as cracks, dents, or compromised coatings. If an embankment is needed, it should be constructed at least 4 feet (1.2 meters) above the pipe. For pipes larger than 72 inches (1.8 meters) in diameter, an embankment is not required. Additionally, underground utilities must be marked before excavation begins. The trench should be excavated to a width that is equal to the pipe's outer diameter plus 4 feet, 1.2 meters. For trenches deeper than 3.5 feet, 1.07 meters, the walls should be sloped at a 1-to-1 ratio to prevent collapse. The trench bottom must be compacted and proof-rolled, with an additional 12 inches, 30 centimeters, of excavation and replacement if the soil is unstable. A bedding layer of 6 inches, 15 centimeters, is required before pipe placement. Pipes must be aligned precisely using string lines or laser guidance, ensuring a minimum slope of 0.35%. Joints should be sealed with caulking or gaskets to prevent leaks. The M40 project along St. George's Road in Preston involves trenching, installing, and welding new water pipes as part of Melbourne Water's infrastructure upgrade. The process includes excavating trenches in the center median, carefully placing the pipes, and welding them to ensure a secure and durable connection. Once the installation is complete, the area is backfilled to restore the roadway. This project is essential for improving water supply reliability and efficiency in the region, while minimizing disruptions to the local community. The Nymatech pipe lifter is a fully mechanical clamp designed for handling and installing concrete sewer pipes ranging from DN300 to DN1250. It operates without hydraulics and is attached to an excavator using a quick coupler. The clamp grips the pipe at its end, allowing for direct pushing into position. The pipe lifter holds the pipe at a 25 prangle, enabling maneuvering around obstacles while ensuring stability and safety. Once positioned, the pipe is pressed into place using the same mechanism. With a maximum load capacity of 3,700 kilograms and a working angle of up to 30 pounds, the pipe lifter streamlines pipe installation. An optional transport stand with lifting eyes and pallet sockets is available for easy handling and storage. Manhole installation at Precast Concepts follows a streamlined process using Hamilton Kent pre-lubricated gaskets for a secure and watertight connection. The pre-installed connector allows direct PVC pipe connection without the need for boot tightening. The process begins by measuring the required pipe length, considering the portion that will be inserted into the concrete base. After cutting, the pipe ends are chamfered and deburred to ensure smooth insertion. Before installation, both the pipe end and the connector interior are thoroughly lubricated. For connecting 2 pipe sections, the spigot end is aligned and inserted into the bell end of the downstream section. The pipe is then carefully pushed into place. When placing the concrete manhole base into a trench, load-appropriate lifting clutches are used. The base is inspected to ensure a level surface before lowering. The outlet and downstream pipe end are lubricated, and the base is aligned and pushed into position until the pipe reaches the rear of the outlet's third step. The upstream pipe undergoes a similar process. The inflow opening is cleared of debris, lubricated, and the pipe is inserted until it reaches the designated stop. Hydrocarbon-based lubricants must not be used, as they can compromise the connector material and water tightness. Adjustments are made as necessary to maintain level alignment, ensuring a durable and secure installation. An internal lineup clamp is an essential tool in pipeline construction, used to align and hold pipe sections in place before welding. These clamps are inserted inside the pipe and expanded to create a firm grip, ensuring accurate alignment and minimizing weld defects. They are particularly useful for large diameter pipelines where precise joint alignment is critical. There are two main types: manual and hydraulic/pneumatic. Manual clamps are typically used for smaller pipe sizes and require human effort to adjust, while hydraulic or pneumatic clamps are powered for faster and more efficient operation in large-scale pipeline projects. Internal lineup clamps improve weld quality, reduce misalignment, and enhance productivity by allowing quick and precise adjustments. Many models come with copper backing shoes to prevent weld burn-through during root pass welding. They are widely used in oil and gas pipeline construction, water transmission lines, and industrial piping projects where high-quality welds are essential. The installation of 54 inches PVC pipe in Burley, Idaho, showcases its advantages over traditional materials like concrete and steel. PVC pipes are significantly lighter, about 2.2 pounds per inch of diameter per foot, compared to 10 to 15 pounds for concrete. This reduces transportation and installation costs. The video highlights streamlined handling as PVC's gasketed joints allow for quick assembly, cutting installation time by 30 to 50%. Unlike steel, which can corrode over decades, PVC offers a 100-year lifespan with corrosion resistance. Additionally, PVC's smooth interior improves flow efficiency, reducing pumping costs by up to 25%. While HDPE is flexible, it requires fusion welding, making installation slower. The footage demonstrates PVC's superior balance of strength, ease, and longevity in large-scale pipeline projects. Installing large water pipes in northwest Denver involves replacing defective pipeline sections with 50-foot-long pipes weighing nearly 6 tons. The process includes placing new concrete vaults underground, which provide access to critical pipeline valves. Advanced technology, such as an acoustic fiber optic monitoring system, is used to detect potential issues within the pipeline. This project enhances the reliability of Denver's water supply by preventing future problems and ensuring safe, consistent water delivery to the community. Fisher Industries' mobile form cast-in-place process starts with grading the wall footing using an excavator. Footing reinforcement is installed, followed by concrete placement, which cures overnight. The next day, vertical wall forms and rebar cages are positioned, and 6,000 psi concrete is poured. After curing, forms are stripped and repositioned for additional sections. The pipeline installation industry in the United States plays a crucial role in transporting oil, natural gas, and other products. The country has an extensive pipeline network, with around 3 million miles of natural gas pipelines alone. In 2023, the cost of land pipeline construction hit a record $10.7 million per mile, a 23% increase from 2022. The United States pipeline and process services market was valued at $1.46 billion in 2022 and is projected to grow at a CAGR of 5.16%. However, new pipeline projects have slowed, with only 4 petroleum liquids pipelines completed since 2023, 3 crude oil pipelines, and 1 hydrocarbon gas liquids (HGL) pipeline. Despite rising costs and regulatory challenges, pipeline infrastructure remains essential for energy distribution, ensuring reliable supply across industries and regions. The sector continues to evolve with advancements in safety, automation, and environmental compliance. Production and installation of welded steel pipe at Northwest Pipe. The production of welded steel pipe at Northwest Pipe begins with high-quality steel coils, which are unrolled and shaped into cylindrical forms using automated forming processes. These formed sections are then joined through a precise submerged arc welding sew process, ensuring strong, continuous seams. Each pipe is manufactured to specific engineering requirements, incorporating customized fittings, elbows, and outlets to meet project specifications. Once welded, the pipes undergo rigorous inspections, including ultrasonic and radiographic testing, to ensure structural integrity. The interior is coated with corrosion-resistant linings, while the exterior receives protective coatings to enhance durability and longevity. These coatings play a crucial role in preventing deterioration from environmental exposure and groundwater conditions. For installation, the pipes are transported to the project site, where they are carefully positioned using cranes and specialized handling equipment. Production and installation of welded steel pipe at Northwest Pipe. The production of welded steel pipe at Northwest Pipe begins with high-quality steel coils, which are unrolled and shaped into cylindrical forms using automated forming processes. These formed sections are then joined through a precise submerged arc welding sew process, ensuring strong, continuous seams. Each pipe is manufactured to specific engineering requirements, incorporating customized fittings, elbows, and outlets to meet project specifications. Once welded, the pipes undergo rigorous inspections, including ultrasonic and radiographic testing, to ensure structural integrity. The interior is coated with corrosion-resistant linings, while the exterior receives protective coatings to enhance durability and longevity. These coatings play a crucial role in preventing deterioration from environmental exposure and groundwater conditions. For installation, the pipes are transported to the project site, where they are carefully positioned using cranes and specialized handling equipment. Large-scale projects, such as the 60-mile, 84-inch, and 90-inch pipeline in North Texas, require precise planning and execution.